Okay, so hello everyone. Thank you, Mauro, for the introduction. So my talk is a bit hybrid because it's made of two parts. So in the first part, I will tell you about the research work we did during my PhD time, and in the second part, it's completely different, and I will tell you a bit about the experiments we are performing now. I'm doing as a postdoc in EPFL. Okay, so let's start with the first part. So I called it light fractional angular momentum. So as Maurizio likes to say, this topic is a bit esoteric. So I think after 3 days where we talked a lot about spin and OAM, basically here I will try to kind of broaden the scope a bit. And I will not try to convince you that this is very useful or has a lot of applications, because I don't know if it's just a curiosity or if it's important for something. This I would be curious to have your opinion on that. So this work was conducted in CEA-Saclay near Paris with the people whose names are there. I think Thierry is actually hiring for postdocs. So if you want to do a postdoc in this CEA center on this topic, please send a mail to Thierry. And as you can see here on this picture, you see that the topology of the landscape in CEA-Saclay is actually pretty trivial. So it was not a great source of inspiration for this research. Okay, so to start from very basic principles, I would like to talk about symmetries. So very simple, if you consider a circularly polarized field of light, okay? Now what happens if you perform a rotation on this field in polarization space? Well, what happens is basically nothing. So you get the same field, but later or earlier in time, you get a variation of phase. And because in that case, a rotation in electric field space is equivalent to a translation in time, this means that circularly polarized beams are eigenstates of the spin angular momentum. Okay, it's very trivial. It also means that every photon in such a beam has a well-defined spin of +1, let's say. The same is true for the OAM, of course, but this time we perform rotations in real space. So if you rotate this beam in real space, nothing happens to the intensity. But the phase varies, and again, you get a translation in time. So Laguerre-Gaussian beams are eigenstates of the OAM. This is good. This we understand very well. I also take the opportunity to show you dynamically what this space-time, this rotation translation in time looks like. So here are two Laguerre-Gaussian modes, L=1 and L=2. The blue arrows are the electric fields over time. So it's a linearly polarized field, and you see that for L=1, you have two lobes which rotate. One lobe, the field is pointing up, the other lobe, it is pointing down. And for L=2, you have 4 lobes which are rotating with that. You can keep this picture in mind. Now what is nice is that you can combine the two symmetries that we mentioned. And for instance, you can define the total angular momentum of light, L plus S, and you can try to find the eigenstates of that. And trust me, if you take a beam with radial polarization, okay, and you perform the two operations in a row by the same angle, you get back to the initial beam with some kick of phase. So this beam is an eigenstate of L plus S. And since L and S have integer values of angular momentum, well, the total angular momentum is an integer, everything is fine. Another question is, can we find maybe more interesting symmetries, a bit less trivial? And I would like you to consider the following beam of light. So in this beam, you have the central point where the polarization is circular. This is in the transverse plane of the beam. You have a point of circular polarization, and about this point, when you make a loop about the center, there is a change of the orientation of the polarization ellipse. So basically, when you do one full turn, the polarization rotates by half a turn. Okay. So this beam does not look very symmetric to me, okay? But actually, it still obeys a form of symmetry. And to see which one, we can consider a specific point in the beam. So here I'm highlighting the polarization state there. And what we will do is that we will rotate this ellipse by some angle, so in real space. So let's say 1/4 of turn. So this is where the ellipse is going, okay? And now we will rotate the ellipse on itself in polarization space by half of that value, so 1/8 of a turn. So what you see here is that once again, you get back to the initial situation. Let's say you can repeat this trick for every point in the beam, and it will work. So we don't have to think more. We know that we have found that this beam is invariant under this kind of weird combined rotation with a 1/2 parameter in real space and polarization space. And so we don't have to think more. We know already that this beam must be an eigenstate of an angular momentum operator, which is L plus 1/2 S. Okay? And if this beam had another topology, okay, we could define maybe a J gamma operator where gamma could be integer or half integer. Okay? This was discovered and defined properly in 2016 by an Irish team. Okay, can these beams actually exist in real life? Because maybe some of you think that maybe we have some kind of problem here. Because with this kind of topologies, I mean, the electric field of light is a vector, right? So at each point, we actually need to draw a little arrow. And you see that if the vector rotates by half a turn, after a loop, you have a problem. You have a discontinuity in the beam, and you cannot connect the polarization back to itself. So obviously, maybe you have guessed that this problem can be solved by using the fact that the beam can carry OAM. So actually, the phase of light can vary across the profile. And so if the phase varies by pi, the field reverses along the loop. And now you can connect back to the starting point. So this little trick just highlights the fact that the topology of the beam is a bit non-trivial. And actually, you can associate it to a polarization Möbius strip in an abstract space. Okay, and actually, it turns out that those beams are very, very easy to create experimentally. All you have to do is to superpose two beams with opposite spin and different OAM values. So typically 0 and 1, or OAM values that differ by 1. So here is an example, L equals 0, L equals 1. You add the two, and you get the beam I was showing you earlier. So very easy. And the J gamma charge, J1/2 charge in that case, is also very simple to derive. You just take L1 plus 1/2 S1, and it's equal to L2 plus 1/2 S2, and it's 1/2. So technically, you can say that this beam carries h pi over 2 J gamma charge. Okay. And again, I think it's kind of interesting to look at these beams now in space-time, like we did for the Laguerre-Gaussian beam. So this is the J gamma 1/2 beam that we just defined. So you see that you have one lobe that is rotating over time. For J gamma 3/2, you have three lobes that are rotating. So if you compare to the integer angular momentum case, you see that we have this nice correspondence between the angular momentum and the number of lobes which are rotating, except that now, of course, the polarization is doing really crazy things. Okay, next question is, can we use those beams to do some nonlinear optics? What will happen? So in my laboratory, we were doing high harmonic generations. That's the only thing we know to do. So I mean, Carlos explained to you very well how it works. So you have an intense infrared beam, you focus it in a jet of gas, and you get a bunch of harmonics in the XUV domain. This is highly non-perturbative. I mean, the physics of this is very rich, but I don't have time to talk about it a lot. OAM alone was shown to be conserved, and spin alone was shown to be conserved in high harmonic generation. Again, this Carlos explained to you in details. And you basically understand it with a very simple and half-true, half-wrong photonic picture of the process, where you say, okay, if I want to emit harmonic Q, I absorb Q infrared photons, and I emit one XUV photon. And so if OAM is conserved, the OAM of harmonic Q is Q times the OAM of the driver. So is it the same for the J gamma? I mean, yes, but okay, let's pretend that there is some suspense. So that's the question we ask, is gamma conserved? So to check this, we prepared a strong infrared beam in this J gamma mode. This is what simulation predicts for the harmonics. So what we see from that is that the topology of the field is actually preserved. We are still in this gamma 1/2 case, sorry. But what about the charge? What about the J gamma? And how can we measure it experimentally? This is tricky because the J gamma is really encoded in both the polarization structure and the phase of the beam. So experimentally, it's very difficult to measure. And the trick we came up with is to use a non-collinear geometry. So what we do is that the two beams that we superpose to get the J gamma beam, we actually have a small angle between them. And because of the conservation of linear momentum, basically the harmonics split spatially. So you see that each harmonic is actually containing two vortices with opposite spin and maybe different OAM values. Okay. So let's do the experiment. This is what we observe. So indeed, each harmonic is a set of two different vortices. what is important is that you see that in the overlap region between the vortices, there are no interference, no fringes, which is not the case for linearly polarized, the linearly polarized equivalent of the experiment. Here you see those fringes that are due to the interference between the vortices. So the fact that there is no fringes is a hint that the two contributions have orthogonal polarization. So actually they have opposite spin, but all we can say is that they have orthogonal polarization. So opposite spin. And what you can see also maybe is that on these beams have a kind of weird shape. On the diagonal there is some modulation. So this is because of our refocusing system, which is astigmatic, and we purposely made it a bit more astigmatic than usual, because when you do this, you have Laguerre-Gaussian to Hermite-Gaussian conversion. So the more astigmatism you have, the bigger the conversion, and the number of lobes, the number of nodes in the profile actually gives you the OEM of the beam. So this is the, if you remember, this is the donut to baguette conversion that we discussed with Sujoy earlier this week. So let's count the number of nodes. So this is on the bottom, it's a comparison with theory. And what we find is that for harmonic 7, we have OEM 3 and 4, for harmonic 9, 4 and 5, and for harmonic 11, 5 and 6. So now we are happy because we know both the spin, I mean, we guessed the spin, let's say, and we know the OEM, so we can actually compute the GAM, L plus 1/2 S. And when you do this, you find that each of the two contributions of each harmonic have the same J gamma, which is 7/2 for harmonic 7, 9/2 for harmonic 9, and 11/2 for harmonic 11. So more generally, we write that the J gamma charge of harmonic Q is Q times 1/2, so Q times the J gamma of the infrared beam. So this is summarized here. So for each harmonic, you have a well-defined J gamma, and those are the black dots, which is fractional and which increases linearly. But what is interesting is that each harmonic is actually a superposition of different OEMs. So the OEM is not pure, the spin is not pure, not well-defined, but the J gamma is indeed well-defined. Okay, and so just to compare with Carlos' talk, so you remember, he was saying that in the case of Laguerre-Gaussian beam, you had this attosecond emission, which has this light spring spatiotemporal shape, and I like to think of it as the fact that you have those two lobes rotating, and they are basically shooting attosecond pulses as they rotate, and so you have this double branch corkscrew. In the case of J gamma, you have only one lobe that is rotating, so you have only one branch. This is a simulation, by the way. We did not measure it. Okay, so what have we learned with this nice experiment? What we have learned is that in this specific situation, the J gamma operator is actually maybe the good quantum number to describe the process. Because our experiment can be fully understood just with the spin and the OEM. But it's a bit annoying because you have to count the different combinations of photons and the different spin and to add them up and to have the results. Whereas if you use the J gamma framework, you have pure modes, so you say, okay, there's just a parametric conversion. Okay, so those results make us wonder if J gamma maybe is just a regular true angular momentum, just like the spin or the OEM. And I'm not entirely sure that is the case, but I think yes, for the following reasons. We have seen that this J gamma operator generates rotation, weird rotations, but still rotations. You can actually prove that those eigenstates of J gamma provides a basis for partial Lie fields, so you can write any Lie field as a superposition of these modes. So it means that you can quantize the electromagnetic field in this basis also. You can also show that the eigenstate of J gamma, they propagate nicely. And what we have just verified is that actually it's parametrically conserved at the photon level. So is this normal? Because, I mean, we know that photons are bosons, so normally they have integer spin and integer total angular momentum. So why is it that now we can magically define the fractional angular momentum for photons? Where is the problem? So once again, I'm not entirely sure of the answer, but I think the idea is the following. Like in other areas of physics, you can also find exotic quantization of the angular momentum, and usually this is related to a reduction of dimensionality. So if you take the example of the fractional quantum Hall effect, where you have electrons that are confined in a 2D plane in the influence of a magnetic field, you can define quasi-particles which also have a fractional, higher order angular momentum, and charge also, I think. And here the situation is a bit similar. So in general, Maxwell's equations are symmetric and there are 3D rotations. But here we are in paraxial optics, so we only describe things in a 2D plane, the transverse plane. And so we have a bidimensional description, which probably allows to do any linear combination, basically, between spin and OEM. Okay, so just to conclude, I wanted to show a bit more about, what are the next steps, let's say, but this Carlos already explained. There are more degrees of freedom to investigate. If you're interested, we can even talk of weirder topologies and weirder angular momenta for light. Okay, that was the first part of my talk. I don't know if I still have a bit of time. Yes, I think so. Okay, so let's totally switch the topic. So I'll tell you a bit what the kind of experiments we are doing in my, this should be EPFL. And that's, they are both red and white. So yeah, sorry about that. So this is a very new lab. Basically, it's been 1 year that we are building the experiment, so the results are preliminary. So those are the people involved in the experiment. We have a collaboration with theoreticians. And there, it's very nice because around Lausanne, the topology of the landscape is a bit non-trivial compared to CEA, so it's a nice inspiration for this kind of work. Okay, so in this lab, basically, our general goal is to try to coherently control properties of quantum matter with light, especially with terahertz light. And so the first project we have is dealing with chiral phonons in materials. So there has been some, so chiral phonon basically is the combination of two orthogonal phonon modes that are degenerate, they have the same energy, same frequency, but they are typically pi/2 out of phase. So you get a circular motion of the atoms, okay? And it was predicted that there would be coupling between those chiral phonon and spins in the material, and this could generate magnetic fields and magnetization. Okay, and so the idea is to drive those chiral phonons with circularly polarized resonant terahertz light, okay, and to probe the magnetic field that emerges from that. So this is theoretical work showing the oscillation of the phonons and the expected magnetic field, which according to theory can be potentially very big. Okay, and the approach we want to have, which is a bit novel compared to the very recent experiments, is that usually what people do is that they drive the material. So they drive the chiral phonon and they probe, typically by Faraday effect, the magnetization, the magnetic field in the same material. And the problem there is that you cannot, I think, actually differentiate between a purely artificial magnetic field, which would be caused by Berry curvature or something like that, from a real magnetic field, which would cause the Faraday rotation. And the difference between an artificial gauge field and a real magnetic field, one of the differences is that a real magnetic field actually extends out of the sample. Okay, and so what we plan to do and what we are actually right now trying to do is that we have the sample where we drive the chiral phonons, and next to it we have a detector sample where we probe by Faraday rotation the magnetic field extending out of the sample. Okay, and we did an early experiment aiming at reproduce the results of literature, so where we pump and probe in the same spot, and okay, there is some signal. It's kind of positive when the field is spin +1, negative when it's -1. But there are some very weird behavior which are not expected, and so all of this is very preliminary early results. But all of this convinced us really that this proximate magnetometry scheme is actually important. Another type of experiment that we want to do is to try to couple OEM terahertz light with superconductors. So maybe you know that if you have a superconducting ring or a hole in a superconductor, the magnetic flux, the flux of magnetic field in the hole must be quantized. And this is because of the continuity of the macroscopic electronic wave function around the hole. And so, I mean, when you see something like this, it resembles a bit typically the wavefront of a Laguerre-Gaussian beam. In both cases, you have a macroscopic quantum phase, let's say. So it's not impossible to think that there would be some couplings. So there are some theoretical works studying the coupling between a Laguerre-Gaussian beam and a squid device, for instance. And the basic principle of this is kind of simple, is that when you have a Laguerre-Gaussian beam, it has a longitudinal B field. And this longitudinal B field can maybe induce currents about the hole and potentially change the magnetic flux in the hole. So the hole goal of that would be typically to say, okay, can we add one quantum of flux in the hole, or can we remove one quantum of flux from the hole using the OEM of light? I mean, I won't go into the details, but one of the problems we think we will be facing is that magnetic field in light pulses is oscillating. Okay, it's positive and negative. So on average, it's not changing anything, let's say. The thing is that with terahertz pulses, we can easily get few cycle or single cycle pulses where you have a strong asymmetry between positive and negative fields. Or you could bias the system with an external field so that you get this asymmetry. And the idea is that if the magnetic field becomes strong enough, if it exceeds the penetration field, then you could allow some quantum of flux to enter the hole, and those would remain after the pulse is gone. So here I'm showing, again, preliminary results where we did the experiment. There is no OEM for now. So here it's just, we had an external magnetic field, and we increased it by a little bit just to show that we are actually sensitive enough to detect optically a single quantum of flux in a small hole. And this experiment there is also interesting. So we have in blue an external magnetic field that is ramping up. And in red, you have the magnetic field probed optically in the hole. And so if you don't do anything special because of this screening, okay, normally the magnetic field in the hole is not changing. Okay? You're totally screening the external field. But here we come with laser pulses at 1 kilohertz repetition rate. And they are strong enough to, by what mechanism, I don't know exactly, but disrupt the superconductivity in a transient manner, and it recovers then later on. So every time a pulse is arriving, there is a bit of flux that is entering the hole. So you have those steps, and slowly but surely you're reaching the external magnetic field. Okay, so for both of those experiments, the chiral phonons and the superconducting flux quantization, you need a source of bright, frequency-tunable, polarization-tunable, OEM-tunable terahertz pulse. So basically, that's been 99% of my work during the past year. So we now have such a source, which is operational, and which is actually a novel in the details of the construction. If you're interested, we can talk about it. It's basically based on different frequency generation between signal and idlers of an OPA. And so we have shown that we were able to tune the frequency of the terahertz. So in this first scheme, from typically 0 to 6 terahertz. And with a slightly different configuration, we went up to 10, 12 terahertz with a strong pulses. And the idea is that in the future, if we want to have OEM beams, I believe that you can just add the spiral faceplate in one of the arms. And because of the conservation of OEM in DFG, I'm pretty sure that you will get, not Lagarde, but OEM beams in the terahertz. This was actually done in a slightly different configuration. And the polarization control is achieved with this kind of setups where we combine polarizers and mirrors. And again, we can talk about the details, but we also verified that we were able to control the polarization of the terahertz in an achromatic way, let's say. So we can be at any frequency and tune so it's like a super wave plate, let's say. And we can go from linear to right or left circular. Okay, thank you for your attention.